and then supplied to phase modulator. So, the extra deviation in the carrier due to higher modulating frequency is compensated by reducing the amplitude of higher modulating frequency. Hence, frequency deviation at the output of the phase modulator will be effectively proportional only to the modulating voltage, and we obtain an FM wave at the output. This is the block diagram of a Armstrong method, indirect method. Here we use an integrator to modify the modulating signal. Then by this modified modulating signal, we phase modulate a carrier, that is crystal controlled carrier, and we get a narrow band FM. This narrow band FM is applied to a frequency multiplier, and we get a wide band FM. So, Vm is modified. So, Vm is integrated Vm cos omega t dt, we get Vm sin omega t divided by omega m. So, in place of Vm, we get Vm upon omega m. Modify modulating signal by the passing through a integrator to change modulating signal Vm into Vm upon omega m. Use this modified modulating signal to phase modulate the carrier, that is crystal controlled carrier. There are two cases. Case 1, let us take the case of phase modulation, that is basic case of PM. Assume that phase deviation or modulation index is equal to 0.5. We already assume that phase deviation must be kept constant and small to keep the validity of this equation. So, according to the equation of phase modulation, V is equal to Vc sin omega Ct plus MP, MP is the modulation index sin omega Mt. So, we get Vc sin omega Ct plus MP is equal to 0.5 sin omega Mt. This equation is solved by using Bessel's function. So, we get number of terms, that is J0, J1, J2, but for m is equal to 0.5, only J0 and J1 terms are existing, that is J0 is equal to 0.94, which is assumed to be near equal to 1, J1 is equal to 0.24, which is assumed to be 0.25 or 0.5 by 2 or m by 2, because m is equal to 0.5. So, Vc from this equation, J0 is taken as 1, J1 is equal to m by 2, we get Vc sin omega Ct plus m by 2 sin omega c plus omega mt minus sin omega c minus omega mt, or we get Vc sin omega Ct plus m Vc by 2 sin omega c plus omega mt minus sin omega c minus omega mt. This result is same as frequency modulation. So, second method, let us take phase modulator, implementation of phase modulation. Let us take the balance modulator having input as modulating signal. So, we get a balance modulator with its output is a double sideband suppressed carrier AM signal. So, we get MVC by 2 cos omega c plus omega mt plus cos omega c minus omega mt. This is the output of balance modulator. This output is passed through a 90-degree phase shifter and a carrier is added to it. So, we get V is equal to Vc sin omega Ct plus MVc by 2 sin omega c plus omega mt plus sin omega c minus omega mt. This is the same equation we get already, this equation. So, by this combination, that is a balance modulator plus a 90-degree phase shifter and a carrier is added to it, we get same equation as we get from the phase modulation. The result is same as PM, phase modulation. Now, if we kept the modulation index of PM less than 1, the resultant is FM as stated in case 1. The resultant is narrow band FM, and by using frequency multiplier, this narrow band FM is converted into wide band FM. This is again a block diagram of this Armstrong method. This is crystal oscillator, we get a carrier from here. First of all, integrator is used to modify the modulating signal. By using this integrator, this applied to a balance modulator and we get a double sideband suppressed carrier signal which is 90-degree phase shifted, and this is added to a carrier. Then by using the frequency multiplier, this narrow band FM is converted into wide band FM. This modulator involves splitting the carrier wave into two parts. One path is direct and other path is through a 90-degree phase shifter and a balanced modulator. Phase shifter gives 90-degree phase shift to carrier used for double sideband suppressed carrier generation. The resultant of this is a double sideband suppressed carrier wave and a carrier is added to it. The output of the balanced modulator is reduced in amplitude, so that is very small compared to the oscillator output. This output is the phasor sum of two sidebands without any carrier and is displaced in phase by 90-degree. The sidebands are added to the oscillator output so that a phase modulation occurs. As audio signal is already integrated before the phase modulation, this is a effectively narrow band FM by the audio signal. Multipliers and down converters are used to adjust the frequency deviation and carrier frequency to get a wide band FM. This transmitter is widely used in VHF, very high frequency, and UHF, very ultra high frequency radio telephone equipment. The carrier in this case is a crystal controlled oscillator having very low frequency. So, due to this low frequency, we need a number of stages of frequency multiplication. One reason for using indirect FM is that it is easier to change the phase than the frequency of a crystal oscillator. So, the limitation is that the modulation produced by this method differs from the ideal in two fundamental respects. Number one, the envelope varies with time due to residual amplitude modulation, because we use a balanced modulator. So, in balanced modulator we get a amplitude modulation. Angle theta IT contains harmonic distortion. These are the two limitations of this method. By keeping modulation index equal to or less than 0.3, these two limitations can be overcome. Last is the automatic frequency control. As we already discussed that all the direct methods we have discussed are using LC oscillator for generation of oscillations which are not a stable oscillator. The oscillator on which a reactance modulator operates must have high stability of frequency. It cannot be crystal oscillator. So, frequency stabilization methods are used for this purpose. These methods are called automatic frequency controlled. Stability is improved by an AFC circuit. The tendency for carrier frequency to drift, which is usually unacceptable for commercial radio applications. To overcome this limitation, the frequency stabilization of FM generator is required, which is realized through an feedback network. This is a diagram of AFC automatic frequency control. Here we use a feedback system. First of all, a reactance modulator which is applied across a LC oscillator, then a buffer, then a amplitude limiter, and we get a FM output. This FM output is applied to a mixture where it is compared with a crystal frequency, crystal oscillator frequency, and we get a difference term, that is Fs minus Fo. Fs is the FM output, Fo is the crystal oscillator output. This frequency is known as the intermediate frequency. It is amplified and applied to a discriminator. Discriminator is a device which gives voltage output depending upon the frequency. So, it is a frequency to voltage converter, and this DC correcting voltage we get from discriminator is applied to reactance modulator to correct any drift in the frequency. The reactance modulator operates on the tank circuit of an LC oscillator. It is isolated by a buffer. Then it is power amplified through amplitude limiter. A fraction of this output is taken from limiter is applied to a mixture. Mixture also gets an input from a crystal oscillator. The resulting difference signal, which is known as intermediate frequency signal, is amplified and is applied to a phase discriminator. Phase discriminator is a device which gives a voltage output depending upon the frequency. Its frequency is usually 1/20 times of the master oscillator frequency. The time constant of the diode load of discriminator is quite large. Frequency changes due to FM are faster than the master oscillator frequency. So, discriminator will react to slow changes in the incoming frequency, but not to normal frequency change due to FM. The discriminator must be connected to give a positive output if input frequency is higher than the discriminator tuned frequency, and negative output if input frequency is lower than the discriminator tuned frequency. So, we get either positive or negative output depending upon either input frequency is more than or less than the crystal oscillator frequency. For example, consider that frequency of master oscillator drifts high. A higher frequency will be fed to mixture. Crystal oscillator frequency is stable. So, discriminator will receive higher frequency. The discriminator is tuned to the required frequency difference. Now, its one input frequency is higher. Its output will be positive DC voltage. This voltage is fed in series with the input to the reactance modulator. This increases its transconductance GM. As transconductance increases, its capacitance C equivalent also increases, and as C equivalent increases, overall frequency, that is 1/2 pi under root LC, decreases. Again, as the input frequency is more than crystal frequency, we get a positive DC output voltage from the discriminator. This is applied to reactance modulator, which increases its transconductance. As its transconductance increases, its C equivalent also increases. Due to this, overall frequency of the master oscillator, that is 1/2 pi under root LC, decreases, because frequency is inversely proportional to the square root of capacitance. So, when capacitance C equivalent increases, oscillator frequency decreases. The frequency rise causing all this activity has been corrected. When the master oscillator drifts low, a negative correcting voltage is obtained from the discriminator, which is applied to the reactance modulator, which decreases its transconductance, which decreases C equivalent, as C equivalent is directly proportional to transconductance. So, as C equivalent decreases, the overall frequency of master oscillator increases. The mixing process makes circuit somewhat complex, but without mixing, proper error signal cannot be generated. The stability of whole circuit depends on the stability of discriminator. So, the stabilization could be lost. To take care of this problem, the frequency of the output of the mixture can be divided. The frequency drift will also be divided. The discriminator can now be tuned to this divided frequency. By using AFC, stability can be improved. The whole discussion can be applied to any oscillator, not only crystal control oscillator. Now, no modulation is fed to the reactance modulator. The discriminator load time constant now be faster. Varactor diode can also be used in automatic frequency control. Thank you.